Thanks all for coming in person or joining online. It's my pleasure to introduce our first speaker for today's lecture in climate data science, Chad Small. He's a secondary PhD, He's a secondary PhD student in atmospheric science at the University of Washington. Chad's current research investigates how multi-scale phenomena can interact to intensify rainfall and consequently potential flooding. He's a recipient of the National Defense Science and Engineering Graduate Fellowship. Outside of science, Chad has spent the last 5 years writing as an environmental justice reporter and science writer in both freelance and full-time capacities. He's currently the climate fellow at the Bulletin of the Atomic Scientists, and his other work has been featured in Grist, Next City, and Gothamist. He holds a Bachelor in Science in Environmental Engineering from Yale University and a Master in Science in Earth and Atmospheric Science from the City College of New York. It's a great pleasure to have you here, and thank you.
Thank you so much for the introduction. So yeah, my name is Chad Small. I'm a second-year PhD student in atmospheric sciences at the University of Washington. Title of my talk is the Madden Julian Oscillation in Atmospheric Rivers toward a new paradigm for S2S forecasts of high-impact weather extremes. My talk is going to be segmented in 2 parts. The first part will go into preliminary research that I've been working on the past year and a half or so. And then the second half is going to be more of a science communication talk where I talk about my reporting and how that can be impactful for the work that we do. Okay, so let's get into the, outline for the talk. So this talk is in 2 parts. I'm going to give part 1 for the science talk. So we're going to go through the motivation. So why am I doing this work? How it impacts West Coast rainfall. I know we're in New York City right now, but my research is focused on West Coast rainfall. I mentioned Madden Julian Oscillation. We're going to talk about what that is and why it's important. I mentioned that in its impact for atmospheric rivers. We'll talk about that as well. And then my research particularly looks at how the Madden Julian Oscillation, or the MJO, uses rain as a moisture source, impacts atmospheric rivers. And I'm going to look at that for flood risk as well. And I'm going to briefly touch on machine learning applications for this kind of research. So, and then for part 2, which is like a science communication talk, I'll get more into the outline in part 2, but I just like presented here so you can see the lay of the land as we're going to go through this talk. But let's move into the motivation. Okay, so rainfall extremes are one of the biggest contributors to flood risk globally. Every year, billions of dollars in damages come from flooding and rainfall extremes, and this often leads to thousands of people dying every year. So this is a big problem both domestically, globally, everywhere. Here I'm showing a picture of Gilroy, California from 2023. As if you guys have watched the news last year, California has got a lot of rainfall and a lot of flooding. And this picture shows homes and trucks and cars and feet of water. So I'm going to get into what's happening on the West Coast and how this is taking place. So let's think about like what flood is. So what I am showing here is a map of spring flood risk from 2023. So what you can see here is you can see in Central California, you can follow my cursor, we have moderate flood risk for most Central California, and then minor flood risk throughout the rest of the state. We have to ask ourselves, like, what causes flood risk? What is the flood risk factors, right? Flood risk is not multifaceted. Flood risk can be natural environment. If you live near a coastline, you might have storm surge from a hurricane cause flood. The built environment is important too. If a dam bursts, that can cause flood. But the last factor is rainfall. Severe rainfall can cause flooding. I know in New York City, in September, we had massive rainfall and flooding that caused subways to not function properly. Parts of Brooklyn were like under feet of water. So we're going to get more into how that operates. So this is the percentage of normal precipitation from October 2022 through March 2023. So if you can see the same part Central Valley, some places are looking at over 150% of their normal rainfall, so what they expect in a given year. So the question we have to ask is, how does that rainfall happen? And a lot of that rainfall on the West Coast is different than how it operates here. A lot of that rainfall is in atmospheric rivers, where in the East Coast, it's usually thunderstorms that take place in the summer or the fall. So then the question becomes, what is an atmospheric river? So this is a map of the Pacific Basin, and you can see the atmospheric river here in this blue contour. So atmospheric rivers move these narrow bands of thousands of square miles of moisture throughout the air. When they make landfall on the West Coast, you can get into a situation where you have lots of extreme rainfall. This is very different on the West Coast than it is out here. This takes place mostly in the winter season, and I'm going to focus on the winter season for the purpose of my talk in the fall. So the cold season, so fall, winter, and spring. So people might look at this and then ask, okay, like Chad, how are we getting this rainfall? What is causing it to be, what's making the atmospheric rivers stronger? Some folks might talk about it from perspective of like El Nino, La Nina, or Enzo. Some people might talk about climate change. Those are all taking place too in the background. But what I want to focus on for the purpose of my talk is the Madden Julian Oscillation, or the MJO, which is in this orange contour right here. So what is the MJO? What is that as a feature? So let's talk about it for a second. So the MJO is this large rainfall disturbance of winds and pressure that moves from the Indian Ocean to the Pacific Ocean. If you're living in Indonesia, for example, you might experience rainfall from that event as it takes place. And ahead of it, you usually have sunny, dry conditions. But the MJO is such a large system, and it operates at this very interesting time period. Climate scale events are usually years or decades in time. Storm could be about a few days to a week. The MJO operates from this 2 weeks to like 2 months time frame. So very unique for the purpose of like weather and climate. It's like a bridge between the climate in the long term and the weather in the short term. So because of that, it has lots of impacts globally for weather anywhere besides that region. So this is a map of the MJO impacts globally. So what you can see here is, if you can follow my cursor, on the West Coast here, MJO can have impacts for wildfire. If you live in Indonesia, for example, it might just flood you out there in particular. It can affect South Asian monsoons. For the purpose of my talk, I want to focus on atmospheric rivers. And the question is, how does the MJO really impact atmospheric rivers? So let's come back to my previous figure I showed before. So now I'm bringing us back, and now I show the atmospheric rivers here, the extreme rainfall again, and the MJO. And let's talk about like what we know. Like, what do we know about this space? So the question we're going to have is, how does the MJO influence atmospheric rivers? And often that's by influencing the background state of the Pacific Basin, right? So one such way you can do that is by changing the jet streams. Jet streams can direct moisture, direct storms in different places. That's kind of what happened in California in February with that big atmospheric river. They can change the heating of the ocean by delivering lots of like water to the Pacific Ocean. And then also lots of research has looked into like this as a modulator of rainfall on the West Coast. So you can see, if you think about West Coast rainfall, people have found that when the MJO is in different phases, it might impact how heavy rainfall might be, whether it's from British Columbia all the way down to California. So the question you ask is like, okay, so what am I doing that's different? What am I doing that's unique in this space? So my science question that will show up is, the MJO is a big rainfalling system. A lot of rain is there, so rain usually means water vapor is present. So I want to know, does that water vapor that's present in MJO could be a moisture vapor source for the atmospheric rivers? If so, does that moisture make these atmospheric rivers different? And then does that make the rainfall they deliver in the West Coast stronger or less strong? That's the purpose of my research. So in order to do that, we got to think about, okay, Chad, how do you track the MJO? Where do you figure out where it's in space? Where do you figure out where atmospheric rivers are in space? And then also, how do we define rainfall extremes, right? Those are all big questions that operate in different spaces in our fields. So let's talk about the MJO for a second. So this figure is, sorry, a little delayed here. This figure is the historic look at the Madden Julian Oscillation on MJO. So Madden and Julian were two scientists at Bachelor of Atmospheric Research. In the 70s, they discovered the system moving from the Indian Ocean to the Pacific. If you look at this figure here, you can see the top shows you where it starts, and you can see how it's propagating through space and time, right? So that's like the historical view of what the system is. But then how do you track it? So the way that it's been tracked has often come from this real-time multivariate MJO index. It's a mouthful, so we call it the RMM index, right? What that does is that takes the primary component of upper level winds, lower level winds, and also like OLR, or outgoing long range radiation anomaly, which is basically a proxy for cloud cover. And it kind of tells you where the MJO is having impacts in space. we have this little figure, this phase diagram here, which goes from 1 through 8. And 1 through 8 represent different parts of whether it's an Indian Ocean or Pacific Ocean. But this is like not really tracking physical quantity. It's more like an anomaly. It's like what's happening here, but not like, is the rainfall here, right? So that's how we do this a little bit differently now. So Brandon Kearns and Shui Chen, who I work with at University of Washington, have started developing and using this MJO large-scale precision tracking algorithm called the LPT. What the LPT does, the LPT, as we can see, sorry. So what the LPT does, we can see in this top portion, this is the rainfall accumulation here. If I can get this to play. Sorry. Oops. The screen sharing, what window close? Sorry. Technical difficulties, give us a second. Give me 1 second. Screen sharing close? I think so, should be. You're okay. Or is this full screen? And we should be okay. Sorry about that, folks. A little technical difficulty. And we're going to try to bring us back to where we left off. There we go. Apologies for that. Let's do, there we go. Okay, awesome. So we're back here. This animation's frozen, but if you look at the top part, this is rainfall, rainfall anomaly and accumulation here. So we can see we're tracking this rainfall on the top. And then as it propagates through time, the more blue this is earlier dates and the red is later dates. So we can see how we can track this rainfall as it propagates through space and time. And that's really how we find out whether MJO rainfall is taking place. But then we think about atmospheric rivers, how atmospheric rivers often tracked historically. So I'm going to start with the previous work and the previous paradigm. So the first thing we're going to start with is total observable water, which is if you were to take all the water vapor from the surface, top of the atmosphere, and just like add it up as like a static quantity, how much water vapor is there present? So that's really been used often to do global tracking atmospheric river features. So the idea is like, where are the atmospheric rivers taking place in space globally? If you want to see this in animation form, we have our atmospheric rivers here propagating through space in these contours, magenta, red, and green. The background of this is a total water background field in millimeters. So we can see how that can be tracked. That's one paradigm of tracking atmospheric rivers. The second paradigm is the vertically integrated water vapor transport, or IVT. What that is, if you take that static quantity of TVW and you move it in space, how fast are you moving how much water vapor? That's another paradigm that's been used. And that's usually used to look at near coastal impacts, atmospheric rivers, focused on Pacific Ocean atmospheric river dynamics, and also global impact of atmospheric rivers. That looks like this animation, where we can see how the IVT background field, which is in kilograms per meters per second, so like massive water moving in space, and we can see how that's been tracked in space too. So that's also like previous paradigms. The way that I want to do my work is, together with Brandon Kearns, we've started to look at these together, look at TPW and IVT together. So the idea is we set a threshold for both variables and then track that as a feature. So here we can see we have this atmospheric river propagating through space. And what you have here is you have the integrated vapor transport contours in this blue, you have the atmospheric river in this magenta, and the background is the total water in this grayscale. So we can see how we can move an atmospheric river feature across the basin. So we talked about Madden Julian Oscillation, we talked about atmospheric rivers. Let's talk about rainfall. That's what we're here to figure out. Like how much is it raining? How heavy is that rain gonna be? So for that, we use the extreme rainfall multiplier. What the extreme rainfall multiplier does is it basically normalizes a rain event against a typically heavy rainfall event. The purpose of this is to give folks like an idea of how heavy it is, right? Like saying it rained 10 inches means something different between New York versus like the Amazon versus California, right? But people know what heavy rainfall is. You know when it's raining a lot outside by just looking at it. So this gives you like an idea of normalizing that. So as you can see here, we have this like equation that uses determinant, where the denominator of this equation is just that rainfall day we think of, or rainfall event we think of. It can be a day or 3 days. I'm using 3 days because atmospheric rainfall develops in time over time. And now we're going to talk about what that means in context, right? This is some work that was done by Kearns and Chen, and also Madden and Chen, who I've been fortunate to work with. So ERM of 1.5 is like flooding, right, in most places. In New York, an ERM of 2 would be taxing our infrastructure. It's like beyond what we can actually like deal with mostly. An ERM of 3 is severe flooding. In California, the West Coast, an ERM of like 1.5 or is like starting to get to the point where things are getting hairy. Hurricane Harvey is ERM of 5. So that's like an extreme case, like truly out of the norm when it comes to heavy rainfall. So what did it look like? So this is a 3-day rainfall accumulation from the West Coast. So if we look here, you can see that in Western Washington, like Seattle's right here, this is the Olympic Mountain Range. We're getting upwards of 6 inches of rain for this 3-day event. It's a lot of rain, right? So, and then out Eastern Washington past the Cascades, it's like 1.5 to 2 inches of rain, not so much rain. Here is the ERM plotted for the same location. So what I want to point out is here. This is 1.5 inches of rain, right? But it's knocking on like one ERM, so a heavy rainfall event in Eastern Washington, because Eastern Washington is not as rainy as Western Washington is. Comparatively, we can see over here, we have a rainfall event at like 4 inches, so pretty significant, but the ERM here is like 0.5. So it's like half of a heavy rainfall event. So this is how we contextualize heavy versus not heavy rainfall events for the purpose of my research. So now that we have all of this done in space, we lay the land of how we do things. Let's talk about how I am tracking my own atmosphere. How am I doing my research? How am I looking at these connections? So my method is connecting the atmospheric rivers to the MJO physically in time and space. Let me clear this out. There we go. So let's start with point 1. I'm going to call point 1 for this. Let's get this back. I'm going to call point 1 for this non-MJO. Non-MJO cases being that we have atmospheric river system here in this contour. The MJO is not present at all in space. What that looks like, if we show it in an animation sense, is we can see we have this atmospheric river propagating in space and time, but there's no Madden Julian Oscillation anywhere present in the Pacific Basin. So this is to show when we have no MJO impacts on our atmospheric river. So that's one way I'm categorizing my atmospheric rivers. The second way is the MJO is active, but it's not connected to the atmospheric river. So we have the MJO somewhere in space, an atmospheric river somewhere in space, but they're separate from each other. That looks like this. So this animation, we show the atmospheric river propagating through time and the MJO out here over the Indian Ocean. It's happening at the same time, but they're not near each other, not connected to each other. That's another paradigm I'm using to categorize my atmospheric rivers. And the reason why I'm doing it this way is because historically, much of the atmospheric river research is focused on the MJO as the NRM index, which doesn't show you physical quantities. Finally, and this is the part that I think is the most fun, is looking at the atmospheric river system as it connects the MJO in time and space, where that overlap takes place. And what that looks like is in this animation where we can see the MJO, the atmospheric river propagating in space, so is the MJO, and they like are in the same time and space as they propagate through space and time. The goal here is to see if the MJO as a water vapor source can just directly get some of that water vapor into the atmospheric river and what that does for our tracking. So now we know how I'm doing it. Let's talk about where these systems are, where their impacts take place, and so on. So first things first, I'm going to show you where my atmospheric rivers are. We're looking at only the winter, and this is from 1998 through 2022. So what I'm showing here is these blue dots are the center of an atmospheric river when the atmospheric river begins, and the red dots are where they end, right? So we have 258 systems for this time period and for the season. I'm only thinking about things taking place in this box. You know, I want to know what's making landfall, and I want to know where the atmospheric rivers are in the Pacific Basin. But let's think about like coastal impacts. So they make landfall, all these cases. And this figure I'm showing you is density. So how often and where do these atmospheric rivers reach their most easternmost point? So how far can they go coastally and where they end up? So what we find, we have many of these atmospheric rivers are going to settle western Washington on the west side of the Cascades, on the Washington-Idaho border, and then in Central California. So now we know like where they're going. So now let's talk about how they break down with my method of categorization for these atmospheric rivers. So first we have our non-MJO cases, and there's not active at all. We have 11 systems. So a small part of that 258. Then we have the systems where the atmospheric river is, MJO is active, the atmospheric river is active, but they're not physically connected with each other. That's 236 systems, so a majority of the cases. And then finally, we have the ones where the MJO and atmospheric river connect in space and time, which is another 11 cases. So most of them are in that like MJO active case, which makes sense. The MJO is most active in the winter, and so are atmospheric rivers. So just like physically speaking, this is kind of what you would expect to happen. So now that we have that, let's talk about what that does to the atmospheric rivers. Go ahead.
Yeah, what data are you using to?
Great question. So the data, this is error 5. Yeah, cool. Yeah, so error 5 for the atmospheric rivers, and then, for people on Zoom, the question was asked what data is being used. So it's error 5 for the atmospheric rivers, and then for the MJO, it's TRIM, so the tropical rainfall measurement mission. Cool. And now let's talk about how these atmospheric rivers might change depending on how they operate in space and time. So let's start with the maximum atmospheric river area. How big are we getting, right? So this blue line we have here is the non-MJO cases. The green line is MJO's active, and the red line is MJO's connected. So this is a distribution of size. So the x-axis is 10 million square kilometers, and the y-axis is like frequency. So how often are we getting these atmospheric rivers taking place across this distribution? So I wanted you guys to focus on the tail end of this distribution, so like towards the end. And what we're seeing here is as we get towards the end, we have the situation where the non-MJO cases and MJO connected cases are getting bigger in size. So let's say that we have MJO connected cases have a little bit of an increase in size, particularly towards the end of the distribution. So they might be a little bit bigger. But let's think about the water vapor that's moved around, how that looks. Let's look at the maximum integrated vapor transport, or the IVT. So again, we have our red is the connected, our green is the active, and the blue is non-MJO. So what we see, look at the tail distribution, and the y-axis here, same density again, whereas the x-axis here is the kilograms per meters per second, or the vapor transport itself. So the distribution is shifting to the right into higher vapor transport, as we can see here at this tail. At this tail, we literally only have MJO connected cases here. So we're getting stronger vapor transport here. And finally, let's look at TW, the static quantity we're looking at for this. So similar thing, the densities on the y-axis, the x-axis is the millimeters of water that's in the atmosphere in these atmospheric rivers. And towards the end of the distribution, we also see mostly these connected cases. So what this tells us is that our MJO connected atmospheric rivers are a little bit bigger, but they contain more moisture and they move that moisture more intensely. But what it tells about rainfall, these are measures of like the atmospheric river itself, not the rainfall present. So now I'm showing the maximum 3-day ERM, so extreme rainfall. And similarly, we can see where our cases are in blue, green, and red. And I also want to show you guys the median of the distribution of the ERM. So what we're seeing here is our interconnected cases are over like 1 ERM higher than the other ones. And we're like triggering at the median some extreme rainfall events in this category. If we look at the tail end distribution, so I want you guys to think of past 3. 3 is extreme rainfall. And we're looking at like very heavy flooding. Only MJO cases, whether they're active or connected, are in that category. So what we're seeing here is increasing extreme rainfall. So interconnected events do lead to increased rainfall, which is really important. Now, the question we have to ask ourselves is, does that rainfall lead to flooding? And I'm going to use an example to show that it might. So this is an atmospheric river case that took place in January 2021. What this animation is showing you is the animation is showing in the orange contour, we have our MJO, atmospheric rivers in this red, and then we have rainfall over here. So this system is developing over about a week, and we see rainfall in this like rainbow contour over here. This is based on Brandon Kern's real-time atmospheric river MJO tracking system, which is this QR code here if you want to check that out and see the work that he's doing, which is really great. Go ahead.
Sorry, for the previous slide, is the rainfall for the total duration of the event once it makes landfall or through its whole?
No, so it's the max after it makes landfall. Yeah, so we accumulate 3 days and then we look at it over land, basically. Yeah, because it's a great question. Yeah, because over the ocean would not necessarily be as important for impacts. So we see how this can impact, MJO can impact atmospheric river downstream. This is a connected case. Now let's think about a case, how this looks over land. So this case is from January 2021. We can see in this figure that we have an overlap for the MJO and atmospheric rivers in space. And this case, when January 2021 hit the Pacific Northwest and led to some significant damage with rain. You have mudslides in Multnomah County in Oregon. We had significant flooding in Portland. And then unfortunately, we had 2 fatalities reported. So now we're looking at a case study for what could happen over land that affects people. So this is why this kind of work is really important. So now that we're here, we have a lot of things going on. And I want to return to the previous presentation. This is just like a snapshot of that previous atmospheric river tracking system. And we have a lot of things going on here. We have atmospheric river and MJO here. We have the vapor transport and TBW in the background as well. And then all of this gives us rainfall. These are all operating in a system. A lot of things are happening here. We have all these variables to track. And to be honest, we're sitting in a space right now where we need high resolution multi-scale models to do this well, right? The MJO is something that needs to be resolved at greater than 2 weeks lead time to give emergency managers the time to be able to prepare for storms and prepare people. So if our model capacity isn't quite there yet, how do we do it? And I think this is how machine learning can help us. You know, machine learning can take some of these variables and help predict them. As I mentioned before, our extreme cases are a minority of cases, right? How do we upsample our cases to be able to make sure our models actually predict extreme events properly? So I think the grand challenge here is how we do this prediction and forecasting in a space where our computing power isn't quite there. So I'm going to leave that as like a question for folks who do that data science and machine learning work. And it's not my research right now, but I think it's good to consider as we move forward. And then I'm going to just summarize some conclusions for part 1. So the MJO, as I mentioned before, has broad impacts on weather and climate, both here and abroad. Integrating it more can really help us prepare folks at longer lead times to deal with rainfall and flooding. MJO precipitation as a water vapor source can be really impactful for atmospheric rivers, which is my own work. And that can really make them marginally larger, but it can also increase water vapor available and making that water vapor much more intense in both capacities. And then that can lead to heavy rainfall events on the West Coast. And then finally, I just want to summarize. So the part 1 is coming to a close. I'm getting part 2 very shortly. I just want to do acknowledgements of the work that I've been doing. So first, I want to acknowledge institutions that have kind of supported my work. I'm a fellow through the ARCS chapter, Seattle chapter of the ARCS Foundation. The Pacific Northwest National Laboratory through the DOE and NOAA and NASA have supported the work that I've done on this research project so far, which has been really great. I want to really acknowledge Shui Chen's research group, which has been really instrumental in getting me ready for research so far and helping me think about these ideas really well as well. And I also want to acknowledge Abby Swan's group for also preparing me to think bigger about research questions as well. So with that, I'm going to pause the presentation and ask questions for part 1. So, questions?
Very interesting. I'm wondering if you could comment on the temporal distribution of those MJO connected rainfall events. Have those been increasing in frequency recently?
That's a good question. So that's something that we're still looking at. There has been some research looking in, I guess I should repeat the question for people on Zoom who can't hear it. The question was, is there increasing distribution over time of the MJO connected atmospheric river events, right? So that's something I'm looking at going forward too, because there's been some research that has been done that's shown that MJO is getting a little bit rainier. as time is going on. So possibly climate change impact there, but not sure. I still need to look to see if that has changed over time. I'm looking more at like how they are in space to just like set the foundation. So currently I haven't looked at that yet, but that's a great question to look at in the future. The questions?
If we don't have any more questions, I think we can go ahead.
Are there questions on Zoom maybe, perhaps? There might not be. I just figured I just check since I can't see this, listen, see anything.
No questions on Zoom right now. But we will have one more.
Yes. Questions.
I hear you say that because of the potential flooding and the different type of conditions that could result from the different changes, like with the MJO and stuff, that we need at least 2 weeks preparation for these activities, like storms and stuff.
So I'll give you, yeah, so the question here was whether or not like the 2 weeks based on MJO timescales, what we need to prepare people for responding for these different types of flooding events. So let me clarify. The MJO operates in this 2 weeks to a few weeks time space, where that gives emergency managers some more time to prepare for these events, right? Climate scale things are on a yearly, beyond yearly time scale, which is like too long, you know, like it's like downstream. It's helpful to know what that looks like in a year-to-year time frame, whereas the weather events can be like a day. Think about like last year in New York, the rainfall fell in a few hours. You know what I mean? You can't prepare for anything in a few hours. If you can figure out on the West Coast, for example, you know, MJO is doing something in the Pacific Basin and you have some weeks lead time leading up to it, that might help people say, okay, we know a month from now we need to have things in certain places to help people not get flooded out, direct evacuations, perhaps for water management. You know, California's had droughts and stuff like that. How do we prepare? We might not get rainfall this year. We might need to like empty out reservoirs to prepare for that kind of stuff. So that's kind of the way that operates.
So at least you're talking about preparing a contingency plan.
Exactly, yes, yeah.
Thank you.
Mm-hmm. Yeah.
Hi, thanks for the great talk. I was thinking if you could like if you had also worked on or thought about the MJO energizing the atmospheric rivers and sort of like changing the dynamic, make them move faster, so you have a pickup of moisture through the wave and they move toward the coast.
So the question, I understand it, was, have I looked at whether the MJO can make the atmospheric rivers propagate more intense?
The dynamic part instead of like just the moisture.
Yeah, so I think so now, so yeah, moisture was step one. The dynamics are coming soon. So I mentioned the MJO can affect the jet stream, for example. So now the question, the reason why I separated into non-MJO and then MJO is active and MJO is connected is the middle part, MJO is active, give you space to think about the dynamics, you know. Is the jet stream going to be more south because MJO is active and stuff like that? Is that affecting where these places make landfall? So that's coming very soon as part of future research. I think that the mechanics and dynamics there are really important for like helping the research space develop. So. Cool, awesome. Thank you, those are great questions. Cool, so in the interest of time, let's move on to part two. So part two, science communication. So I'm gonna lay the land here with my reporting journey first, then I'm gonna talk about atmospheric river reporting, because I just talked about atmospheric rivers, like how we talk about that in the news, for example. Then I'm gonna go into elements of popular science writing, how that done well or not done well, or should done better. And then I'm gonna go into taking the MJO atmospheric river situation and translating it into a story. And then I'm gonna talk about how this can impact researchers. How do we think about communicating as researchers? So I'm gonna start with part one, so my journey reporting. So I'm gonna show a timeline here to just let you guys know where I am in space and time. So let's start with 2016. So I finished undergrad in 2016, and then I got a job as an engineer, so civil environmental engineer in New York City. So I did that for about 2 years until 2018. So that was really good and a really cool way to use my degree to like help folks in New York City. But then I had a little bit of a change of focus. I left that job trying to figure out what I want to do next with my life, which is a hard question for a lot of people. So then I started moving into the reporting space in 2019. So this is a story I wrote for Blavity, looking at Canarsie, which is South Brooklyn, and how they responded to Hurricane Sandy and thereafter, right? So context, Canarsie is a very Black neighborhood in Brooklyn. It's a very West Indian neighborhood. My family's West Indian, so I have connections there. And I was really curious to see how this community dealt with post-Sandy recovery. Sandy had done a lot of flooding to the area. So this is when I was like, okay, let me start writing, like someone mentioned that I can write and know the science somewhat. So maybe it's a space to do more of that. So that's kind of my step one in my journey. But then, I was an engineer for a while. Let me lean on that engineering background a little bit too. This is a story I wrote for Next City in 2020-ish, and it's looking at how this program in Florida helped people retrofit the homes to save energy, but also save costs. So kind of like a green decarbonization story. And for me, I was very much thinking about, okay, climate change is a multifaceted problem, how we decarbonize to help folks. And as an engineer, I kind of understood the space a little bit better, and I could probably talk to people to make that happen. So that's the second step. And then, so as I was reporting, I was like, I want to know more about these climate impacts as they propagate. And I was like, I don't know enough. So I went back to grad school, went to City College in New York, did my master's in Earth and Atmospheric Science. And towards the end of my degree, I was doing my thesis for about 6 months. I got a job working at GRIS as the data fellow at GRIS. And this is when I started to really get into the atmospheric science and the weather reporting space a little bit more. So it's a story I wrote in 2022, looking at how spectrum use, so 5G for your phones, can kind of interfere with the way that satellites can track water vapor and therefore impact our forecasting for rainfall events. So this is about a few months before I went to UW for my PhD. So I'm now doing my PhD at University of Washington. And I've been very fortunate to be a Hunt Fellow at Bulletin Atomic Scientists. And here I really got more into like, okay, let me lean more on what I know. Let me write about the science that I actually know, which has been really cool. And that's been a really edifying and great experience so far. And with that in mind, now I'm going to talk about how do you take what you know in the science space and the reporting space and think about where stories aren't found, where stories aren't seen. So I want to talk about atmospheric river reporting space. Where is it? Where are we? I think this is important as we move forward through this talk. So before I get into it, I know this is weird because it's a lot of science people in here, but before you got here this morning, how many people knew what MJO was before you walked into the room? Raise show of hands. Okay, half the room, so pretty good actually. All right, how many people have heard of El Nino before, La Nina? Raise a show of hands. Basically everybody. How many people have heard of climate change before they got into this room this morning? Yeah, I hope the whole room. Right, exactly. Right. This is really important though, because the MJO space was kind of, you guys didn't know about it before I got here this morning, right? But you're not alone. Here's some reporting on atmospheric rivers from, this is the Washington Post on the left and NPR on the right. They're talking about climate change. Climate change is a big contributor to atmospheric rivers, not the only thing, right? And then you have these two articles from the New York Times looking at El Nino, La Nina, and atmospheric rivers. Also really important, not the whole thing, right? So I'm sitting here thinking, okay, MJO is not really part of this conversation. How do we fix that? How do we get that to be out in the news? But to do that, you think about what it takes to communicate science for popular audience well. So I'm gonna go into elements of popular science writing, which I pulled some of this from the Nicholas School at Duke's School of the Environment's Communications Lab. I didn't take everything, but I found one of the things I thought were most interesting. So I'll start with point one, writing stories, not topics. MJO is super interesting as a scientist, really had a lot of impacts. It's not a story, right? People want to hear about people and those are stories. So how do you make that happen? At the same time, story has meaningfulness. Meaningfulness has to be at the beginning. People get okay, where's the rest of the story? Where do I go? Hook them immediately. And then beyond that, you want to talk about, so same point, top heavy. As scientists, we write papers and our abstracts tell the readers what's going on, why it's important. Same thing is true in journalism too. We start at the top, let them know what's happening. And then a little bit different, a regular reader isn't going to know how the jet stream is impacted by upward divergence and stuff like that and those kind of scientific terms. So bring it to the audience's level of understanding. And I think that's really important. But at the same time, the audience knows, they know things. Don't dumb it down too much. Your audience can really and truly take from what you give them and learn more, become better. Science communicators, science receptacles, like people who understand science. And all of this kind of breaks down into why the story matters, why story is important. So to that end, I am going to talk about the story that I worked on this morning, that published this morning at the Bulletin of Atomic Scientists. This story is how an obscure atmospheric phenomenon, MJO, causes catastrophic flooding in California. So I have the story link here in the QR code. I'll have the QR code link for every slide about the story going forward. But I also want to thank Jessica McKenzie, who's right here as my editor, for like helping me with the story right now. So yes, let's get into it. How do we use this story to show a case study of how we talk about science for people who aren't scientists? So the first thing is write stories, not topics. So this is the first paragraph from the story that I wrote this morning, right? You want to lay it out. People want to know like what is happening in this community, like what's taking place. They're like, oh, this lake dried up. Like, why is it refilling? So let them know, like the lake is dry, but every so often it refills, and when it refills, it leads to catastrophic events, right? But people like, okay, no, now I know this is important. And then like, what is causing it to happen? Atmospheric rivers is causing it to happen. You answer their question. You told them, you laid out the problem, so you have like a what, you have a why. You don't have a how yet. How is the story? But to the point, you only have 10 seconds to convince your reader. Put it in the top, let people know that this is important. That's the first part, right? Now I'm gonna go into a different way. I'm gonna pull back a little bit. So if you wanna show the how or like the why, I think pictures help a lot. So this is the seasonal precipitation outlook from NOAA from the first part of 2023. So what this is showing is green means more rainfall or more precipitation, brown means less, so drier conditions. I want to focus on California. So if you look at California, you assume that the southern half of the state would have been pretty dry last year. If you watch the news, that wasn't the case, right? So what's going on? Why is this happening? And I think this is the question the story can answer for you. So this is paragraph 2. So in paragraph 2, I'm literally going to lay out, here, why is this happening? Why is the fiction not quite accurate? It's because NOAA's forecast looking at ENSO conditions, El Nino conditions, right? Really important for our forecasting space, but not quite the whole picture. So now we know like why we're missing this picture. My reporting fellowship is about climate change. So I always want to bring it back to like how climate impacts are important. And one of those big questions is going to be, if we have a problem predicting these heavy rainfall events in the current context, then that implicates how we can do it in a future context where we might have more extreme events as climate change progresses. Important readers to read too. And this is the second paragraph. Top heavy is good. Bring it right at the beginning. Here's what's going on. Here's why it's important. Here's what it can mean long game. So now people, okay, we know the how is a solution. People like to know how to solve problems. So here, I'm showing them like we can actually solve this problem. We need this bridge though between weather and climate, and how do we do that? The MJO is our answer. So this is the first 3 paragraphs of the story where we basically like have like a what, a why, kind of a how. So people want to know more. They want to know, okay, what's going on in the story? What's taking place? Why is it meaningful? Why is it impactful? And so the NGO is our main character for the story, right? Our main character isn't the character, it's this phenomenon in the ocean. So how do we illustrate this? So I want to show this animation that I was fortunate to. So this animation is predicated on work by Brandon Kearns and our research group who looks at these MJO atmosphere group connections. So this is his research product. You can use a link at the bottom to look at it in more detail. And I want to thank Eric English and Thomas Galkin for putting together this beautiful animation. So we have atmospheric rivers in this red, we have MJO in this orange, but how we have text. Over here we have text that's literally describing what's happening. People can zoom through the story, read it, and it tells them what's taking place in this background space. The images are doing the work for us, right? They're helping people figure out how this is affecting rainfall, why that's meaningful, all those kind of questions. And this is how you get this question of communicating without jargon, right? So we have, avoid big words and jargon. We have very clear text on the right-hand side, but also don't dumb it down. This is a research product that's being conveyed for a popular audience, so people can look at it and see how atmospheric rivers and MJO operate in space to create rainfall. So this is how we get into that space. So now we have our what, our how, our why, our main character, and then we get back to like, why does it all matter? Like why story matters. So for me, stories matter because people matter, you know, like what does this have to do with people? So one of the things that's really important is MJO forecasting can help us really think about getting these longer lead time forecasts. That's super important for how we operate in forecasting for severe events. The reason why is people who don't have resources, often people of color who are low income, can't respond as well to heavy rainfall events or catastrophes, for example. And I want to stop here and pause for a second. My ethos for reporting has always been about helping people learn more, helping protect people who are vulnerable. So I'd be remiss if I didn't mention that I'm in solidarity with students at Columbia and elsewhere who might be, you know, threatened with being arrested for peaceful protests or being arrested. I think it's meaningful to show that our work, scientists and otherwise, is not in a vacuum. It exists in this context of current events as well. So back to that and why that means so much more here in this story as well, is we have a community in California in the Central Valley. And this community of Alpa, it's mostly Latino, very low income. Jeffrey Mount, who I spoke to for the story, mentioned to me that the most communities in Tulare Lake were able to recover decently well after last year's like atmospheric rivers. This one was not able to. It's because they're a low income community and they also have a like impending climate crisis on the way, right? So we have flooding from the lake, but like atmospheric rivers can also snow. So now you have snowpack in the mountains. You get a heat wave now that melts the snow. So you have runoff down the mountains. So now you have flooding from the beginning, a heat wave, and more flooding. So and these are people who couldn't deal with it in the first place. So this is kind of come back to the question of how do we really like care for our communities with our science? And how do we communicate that to the public that's not necessarily us? Finally, I'm just going to come back and show you if this video decides that it wants to play. There we go. I just want to give you guys a little bit of an example of what it looked like. I'm going to mute this. I don't think the volume's as important, but this is what it looked like in that community. Like, it looks like there's an ocean in the street. So this is what people deal with when we have these events. And this is why longer term forecasting is so important. You can help people evacuate. You can think of like, do we have to like release some of our dam water to be able to deal with some of these extra water coming in? Think about having to drive a truck through that kind of water. It's really difficult, it's really dangerous. These are all really, really important things to consider as we think about how our science helps people, but also how communicating our science is even more helpful. So I'm just gonna move on next slide. I just wanna give you a lay of the land here. So let's come back. Pause this and let's go on to the next slide. So it's funny enough, I'm in the process of trying to write up what I'm researching right now into like an academic paper. And as I was doing this presentation, I was thinking, you know, a lot of these things are actually good for scientists too, to think about, you know, it's elements of just science writing, you know. Scientists find interesting things curious, and those curiosity is story, right? You know, people who Einstein found space and just all these other things like physics important as a story. You hear story all the time, right? So we're writing stories on topics. I mean, similarly, your abstract or like beginning of your paper or research is like, why does it matter? Why is it important? Scientists should keep that in mind too. Why are you here? What does your research mean to broader communities? Same thing, top heavy is good. Tell people why what you're doing moves the needle. Why is it important? Why does it feel something we don't know in the space? It's tough because, you know, your peers, your jargon is lay the land, right? You know, we have our language that we use with each other, which is important. At the same time, you can use your jargon or your context-specific language without being overly complicated, right? You like use your terms you know, but the language can still be clear. And similarly, like we're in a space of growing and learning, so you always want to make sure that your audience can like learn more as you do science too. And I think this boils down to like, why does the science matter? And I think as someone who comes from a science background, but also does like reporting, for me, it's really interesting. It's really always important to think of like, how do I bring my science into my writing? How do I bring my writing thought process into my science? I think the synergy there because, you know, scientists are curious people. So as reporters, it's the same job. It's fact finding. You know, we're looking for facts and just a different way of finding those facts. You can find it whether you do like interviews or whether you do your own research. These are all the same skills that go hand in hand with each other. And to that end, I'm sure there's some folks in the room who are scientists who want to think about how to get involved in science writing and communication. So I'm going to give a few examples of how you can do that. There are media trainings in a lot of different places in the country. The Metcalf Institute at the University of Rhode Island has a science communication career development training workshop, which I think is great. AAAS, the Association of American Arts and Sciences, also has an excellent communication science workshop too for folks who want to think more about communicating their research. If you want to enter it, so like the first two are if you want to communicate your science so other people can then communicate it broadly, but just know how to talk about your science and why it's meaningful. If you want to get into the space itself and be actively part of it, the Open Notebook, which is a great consortium of like science writers and stuff, has this great like master class on science journalism, which is awesome. Bulletin Atomic Scientist is great. The editors love working with scientists to help scientists figure out how to communicate their like work for a popular audience, which is awesome. And then there's conferences too, if you want to just like get in space of thinking about these questions. ComSciCon is a conference for science, for graduate students in sciences in the country. They have different locations in different parts of the country, but also they have national conference as well that I think is great. I went last year, wonderful time, learned a whole lot. National Association of Science Writers has a Science Write Conference. I believe this year's November in Raleigh, North Carolina, which is awesome. Just science writers, and a lot of science writers are former scientists or current scientists who still write. And then finally, the Investigative Reporters and Editors has a conference called NICAR. I think if you like math, NICAR is fun. NICAR is a bunch of data scientists who are in a room just trading notes about how to do data science communication for journalism, and it's like so much fun. When I was there in 2022, and when I was there, I had a problem with a programming thing for my master's thesis, and the people from BBC's climate desk fixed it for me in 2 minutes. And these are reporters, like, you know, like these aren't necessarily people who think about it as like proper data scientists, but they do data science so well. So that's kind of like where I am in terms of this. And I want to acknowledge some folks that are important to my journalism journey too. Bulletin Atomic Scientists, like for one, Jessica, John, Thomas, Eric, great people. The whole community of people has been really instrumental in my growth as a science writer. I want to thank SJ, Social Journalism Network, and the New Kind Coalition. They were some of the first institutions to like believe in my reporting when I first started. Also, the editors I've had all over the place, whether it's at Bulletin or at Grist or wherever, they've also helped me grow as a writer. And then I want to highlight the Uproot Project. The Uproot Project is a network of environmental journalists of color. Geosciences as a science space isn't that diverse, as people might know, but environmental reporting also isn't diverse, so there's a diverse problem in both spaces. And Uproot Project has been a really great way to help reporters of color who write on the environment have just like more of a foundation for growth and more community of each other to like learn and share and just grow. And with that, that's the end of both talks. StoryLink is right here, and the Brendan Kern's real-time atmospheric river tracking system is right there. The QR code too, if you're interested. And then, yeah, questions.
Hi, Chad, thank you. My experience with a lot of scientists is that they think about communication as an add-on, secondary, someone else's job. Can you speak to how, not that we're encouraging everyone to necessarily have another full-time job like you've taken on, but how is learning about science communication informed and maybe improved your science, the kinds of questions you ask, and to what extent have your engagement of communications involved speaking with various stakeholders and kind of understanding what parts of the problem are significant to them, what kinds of questions they have? So how do you engage in science communication, and how has it sort of impacted your science, the science itself?
Okay, can people on Zoom hear or should I repeat it? Perfect, okay, awesome. That's a great question, a lot of parts of that question. I guess I'll start with how it improves my science. So it's funny because atmospheric science is a really interesting space because a lot of theory, you know, for like many years we didn't have observations, so theory built the field out. Now we have observations, satellites are here, radars here, we can see different things. And it's funny to me in the context of what are these ways to fact check ourselves, right? How do we find things we couldn't see before? And to me, when I talk to people who are in the community dealing with these like big issues, I am like, oh, you know, I didn't think about this person who lives in this community and they're dealing with like this rainfall problem or this flooding problem. And then it makes me go back, okay, why are they dealing with that problem? Is there some kind of way I can find the science of why they're in that space, which kind of goes back and forth. Even on the other side, as a reporter, I think if you're a scientist in the reporting space, you see questions that other people don't see, and you see them earlier. You know what I mean? Like things don't happen for an accident. So sometimes you see like this these trends and these maps that you're looking at, whether it's like rainfall maps or like EXO, for example. I was thinking about the story that I'm still in my head a little bit about, but there's this whole question of prevented planting. So like the idea of like, if a lot of rainfall in the Midwest, farmers can't grow their crops. There's a lot of cornfields also in South Carolina. And I was looking at the map of where those places were. They're also mostly black areas in South Carolina. South Carolina also has a lot of hurricane risks. So I was like, oh, we have stacked risks here, but only one of those risks comes from like a non-science thing. And like those risks can probably like accumulate to hurt folks, right? So to me, it's really a question of like, okay, how do I take what people tell me to think about science questions, but also how do I take my science to find more stories? And I think for scientists in the space, I think like we go to conferences, you have like AGU, AMS, all these conferences with each other, and we kind of communicate each other, get ideas for research and stuff. And I think people who aren't in our space ask questions that we wouldn't even think of. And I think as a reporter, I get to hear those questions, and it helps my science get a little better. Yeah. Questions? Okay.
Yeah, I had a question about your reporting
Mhm.
and your funding that you acknowledged at the end of the first part of your talk. Does that ever clash? Because like my understanding is that, you know, federal money, federal employees, they have a limit on what positions they can say and put out there. So I just wondering if you could speak to that.
Yeah, I think historically I've tried to keep them separate. You know what I mean? In terms of reporting on things that, well, it's a two-pronged thing. I like reporting on things to learn new things. So reporting things I already know doesn't let me learn new things is one side of it too. On the other end of it, being grad student is a little bit of a weird situation because you're funded by certain things, but also like it's different than working for the agency and stuff like that. I haven't had that clash for me so far. But I also make it a point when I like speak to sources, particularly government sources, let them know that I'm writing certain things because I think it's important for them to know. Also, like what I find is when my reporting, I kind of get into things that people don't think about. And for all these agencies, people knowing what they do at deep level is good for them because it helps people like, oh, NOAA does this. Maybe we should support NOAA more with more tax money. You know what I mean? Maybe these agencies do things that help us. So to me, I see it as like it helps agencies too. They'd be like, oh, you do this forecasting. Maybe people at NOAA want to make their forecasting different. Having the public know that that's a thing allows them to advocate for their members of Congress or whoever to make that more possible. So I think it's a kind of a synergistic thing because like I'm outside the space, but also know the space. It's kind of complicated like paradigms to straddle, I guess. Did that answer your question? Cool. Other questions?
Great talk.
Great, Mike. Yeah.
Great talk, and it's great to meet you in person.
Nice to meet you too.
Actually, before coming, I'd looked up Chad Small because I didn't know much about his bio, and he had written an article for Grist a few years ago, and like just to provide more background, like he like and like I apologize if I incorrectly summarize it, but like he wrote a great article about like how like even though 5G is really great for many or a lot of Americans, but actually it has detrimental effects in terms of like weather forecasting for specific events. And I loved your article, so thank you so much for writing that. And I understand from the article that there are scientists who are like looking to, you know, try to like prevent the US government from like auctioning off 5G. And I'm just curious, like, do you know if there's been any progress in that? Have you been called upon to like maybe like also talk because like
it's so funny. I haven't followed it closely since. So context, I did a fellowship when I was like working in Congress doing science policy tracking work, which is kind of how I knew that was a topic of interest. I haven't followed it since though, so I'm not sure where that is in space. I do know a lot of scientists have been really, really interested in like not having that happen because as you can see, forecasting is important for like lives and livelihoods. I think if you want to track it, the best way to do it, they have, I want to say it's US like Gov docs, US Gov, something like that. I can tell you after the exact URL, but that's where you can track issues and see where they are in Congress, like where they've been introduced, passed, stuff like that. Also, most committees who have jurisdiction over different parts of the federal government, like whether it's NOAA, NASA, whatever, they usually outline on their sites what type of legislation they're trying to pass, what issue areas they want to move into. That would be where I would look to see where it is right now. I'm not really sure myself.